Hi, my name is Kietzmann and I will present our paper Long-Range ICN for the IoT, Exploring a LoRa System Design. This is joint work with José, Dirk, Thomas and Matthias. What is LoRa? LoRa is a wireless long-range technology that transmits data over multiple kilometers with little energy requirements at the order of millijoules. Thereby, the throughput is very limited at the order of bits per second. In more detail, LoRa defines the chirp spectrum modulation, which makes it robust to interference, multipath fading, Doppler, etc. These properties make it an attractive technology for the constrained IoT, where nodes are battery operated and send data sporadically. What is LoRaWAN? It is probably the most popular communication system for LoRa devices, mainly to upload IoT data to a server-based infrastructure. A vertically integrated LoRaWAN network consists of four entities. Application servers provide interfacing to business logic, interconnecting local LoRa networks and data sharing. Network servers interconnect LoRa nodes and applications. These network servers are the core of the network and deal with message routing. They organize communication centrally, including message deduplication and MAC packet scheduling. Gateways are merely relays to the wireless domain. And finally, nodes or end nodes that can operate in one out of three different operation modes. Class A is purely uplink oriented, allowing for maximum device sleep. Nodes send packets using the best effort Aloha protocol. This is followed by two subsequent receive slots, the only way to get data to a node. The network server queues and schedules these downlink packets centrally. Class C operates similar to Class A but leaves the node always on. This allows for permanent downlink but is not an option for battery-driven devices due to high energy consumption. Class B is a trade-off between both and adds periodic downlink slots. This operation mode is barely deployed and suffers from reliability and scalability issues. The Class B vulnerabilities have been analyzed by recent work. Now to conclude. The unreliable uplink communication in LoRaWAN leads to unbounded end-to-end latency. Centralization around the network server prevents edge scenarios and complicates data sharing. This motivated us to aim for a better integration of LoRa devices into the Internet of Things. To overcome the LoRaWAN limitations, we propose a system redesign which consists of two components. First, a new network layer. We base our work on Information-Centric Networking. And second, a new MAC layer. We base our work on the IEEE DSME MAC that we utilize for LoRa-based media access. Now in the following few slides, I will give you a brief introduction into both technologies. ICN is a future internet architecture which displaces the current end-to-end paradigm found in IP networks with a content-aware or information-centric approach. Data is accessed only by names. A hop-voice data transport is based on request-response paradigm, namely interest and data, and allows for ubiquitous content caching on routers in the network. There are different ICN flavors, and we focus on NDN, named data networking, in our work. Three main data structures exist: the forwarding information base, the pending interest table, and the content store. A consumer application sends an interest packet for a name. This interest is forwarded according to a forwarding entry in the FIP until a node serves this interest from its content store. It will not be forwarded if the PIT lacks an entry for that name prefix. On interest reception, each forwarder allocates a pending interest entry with two purposes. First, a subsequent interest for that name will be aggregated and not forwarded again. And second, the data packet returned by a producer follows the reverse routing path noted in the pending interest tables. So, with data on the reverse path, every node consumes the PIT entry and adds the content to its own content store up until the data arrives at the original requester. A subsequent interest for that name from whatever node in the network can be served from any content store. We think that this paradigm has many built-in features that can assist in dealing with the challenging LoRa domain. Most prominently, built-in caches assist in reducing wireless link utilization, which facilitates node sleep and also helps in decreasing the latencies. On the counter side, ICN lacks a lower layer definition. For that reason, we include the 802.15.4 DSME MAC layer in our system to enable robust communication with sleepy LoRa nodes. A coordinator starts network formation and emits beacons in a predefined beacon interval. A built-in resolution mechanism avoids beacon collisions from coordinators in reach. Beacons initiate a synchronized multi-superframe structure. One superframe in the multi-superframe consists of three periods. The beacon period, which can be overloaded with payloads. The contention access period, which enables sporadic communication on a common frequency channel. Sending nodes employ carrier sensing before transmissions. Battery-driven nodes would mostly sleep during that period to save energy. Conversely, sleeping makes them unavailable for the coordinator during that time. And third, the contention-free period, which provides 7 guaranteed time slots multiplexed across 16 radio channels. These slots provide a deterministic maximum latency. Now let's get started with our long-range ICN system design objectives. In our deployment scenarios, an application on the internet consists of the consumer application and can access LoRa data directly without the need for application layer gateways. A local wireless network is served by a LoRa gateway, the coordinator. These gateways act as layer 3 routers and include ICN caches instead of just bridging to a network server like a LoRaWAN. We consider a fully distributed model by shifting more logic to the edge. LoRa nodes implement ICN consumer or, much rather, producer logic to reflect IoT sensor data retrieval as well as control scenarios and node configuration. Our high-level design goals are the following. First, not requiring changes to the rest of the regular ICN network. Second, providing a set of interaction patterns for data transmissions between the regular network and LoRa-ICN nodes. And third, leveraging the low power and long transmission range LoRa-PHY optimally. The resulting ICN stacks for nodes, gateways, and internet applications are visualized on this slide. To evaluate our system, we have developed a simulation environment for LoRa-ICN, which is based on OmNet++ and the INET framework. Thereby, we have combined existing implementations, namely CCNSIM as an ICN simulator, OpenDSME for the Mac, and FLORA, the radio propagation model. In addition to that, we have modified the core implementation of CCNSIM to match IoT traffic, and we extended it by 2 network layer primitives, indication and push, to reflect sporadic IoT data generation better. These cases will be visualized a bit later in this talk. CCNSIM lacks the concept of a link layer, which we added to transmit packets through the wireless transmission system. This module further includes all logic for ICN to DSME. And finally, DSME LoRa integrates the LoRa-PHY with the DSME MAC. For our evaluations, we utilize static packet scheduling for the contention-free period. In bidirectional communications, like interest data, each transmission slot is followed by a reception slot. This halves the number of available slots in the DSME multi-superframe compared to unidirectional schedules. We consider 2 design options in our work: data from node, which is a prevalent use case for sensor data retrieval, and data to node, which reflects the case for node control or firmware updates. We exclude data to node from this presentation. Further information can be found in our paper. For data from node, we distinguish 2 cases. First, gateway-initiated traffic, which reflects request-driven interest data exchange naturally. And second, node-initiated transmissions, which include aforementioned protocol extensions. Now let's have a look at each of these protocol flows and how they map network layer traffic onto DSME primitives. We first consider the case for broadcasting the interest packet utilizing beacons. This appears like an efficient approach, since beacons always have to be transmitted and received to maintain the slot frame structure. Thereby, we distinguish 2 options. Payloads are either overloaded onto the beacon packet, or pending data on the coordinator is indicated in a beacon. This DSME built-in mechanism is known as undirect transmission and allows nodes to sleep during the contention access period. After receiving a beacon indication, these nodes will wake up during the subsequent contention access period. The coordinator transmits the interest therein. While beacon-based transmissions provide unique opportunities for downstream multicast, they are tied to the slow beacon interval, which is 120 seconds in our case. A unicast interest data exchange in the contention access or contention-free period utilizes the DSME structure most naturally. Sending the interest request during the contention access period requires the nodes to turn on during that period, which consumes energy and is not desired in many use cases. Data can return either in the contention access or contention-free period. To reduce the wireless link utilization, we have added a local push mechanism, which allows constrained nodes to directly place content in the gateway cache, which acts as a custodian for these nodes. Similarly to the previous case, data can be sent either in the contention access or contention-free period. A request from the internet can then be served directly from the gateway content store. Lastly, we have analyzed a mechanism where constrained nodes indicate their content availability, followed by a standard request from the gateway, not to violate the request-based nature of ICN. Potential mappings follow the same logic as before. Our analysis showed that the additional packet on the slow link introduces a notable overhead that we consider infeasible. In the remainder of this presentation, we will thus focus on the standard request case initiated by the gateway and the local push case initiated by the LoRa node. We evaluate the completion time for different deployment scenarios and start with a naive content interval of 30 seconds on average per node. Every content item is requested once, and the content rate follows a Poisson process. Data losses result in infinite completion times. That means the end value of each graph also reflects its success ratio. In a small deployment of 7 nodes, transactions that utilize only contention media access finish in less than 7 seconds, which is the duration of a multi-superframe in this case. That means all interest data packets succeeded in the first contention exit period that occurred. Using the contention-free period for either interest or data increases the completion time to over 10 seconds. Still, all requests succeed and finish within 2 multi-superframes. Pure contention-free mappings reveal a uniform latency distribution and a slightly increased completion time. This is introduced by certain interest requests that have to wait for the next contention-free period in order to be transmitted. In larger networks, all mappings reduce their success ratio to less than 40% and the completion time increases to hundreds to thousands of seconds. This is a lot even for LoRaWAN deployments. Now why is this? Contention access suffers from collisions and CSMA retries distributed over multiple multi-superframes. Contention-free media access suffers from queue overflows on the gateway. If we compare the local push and its contention access mapping in particular, the case clearly outperforms the request-based scenarios. This is an effect of the reduced link load. For large networks, queue stress is still notable at the slowly increasing latency slope of the contention-free graph. To summarize, transmitting with contention access is comparably fast in unchallenged networks but is subject to collisions. Contention-free access is more reliable but susceptible to MAC queue overflows. Our unsolicited push outperforms an interest data exchange, reducing link utilization. Next, we set up a more realistic scenario which does not pressure implementations and the wireless domain. Thereby, our content interval is 900 seconds or 15 minutes on average. This reflects common LoRa cases well, in which nodes sometimes only produce data every hour or even a few times a day. Request-based mappings perform similar in small and large networks, only with increased latency. In the 56-node case, all mappings now finish in less than 120 seconds, inherited from the DSME multi-superframe structure. Contention access mappings seem beneficial on the first side, but have 2 hidden caveats. First, downstream interests prevent node sleep, and second, transmission resources are not exclusive and operate on a single channel. In reality, they might still be subject to collisions. Furthermore, MAC management traffic, like slot negotiation for contention-free resources, still has to be transmitted with contention access. The full contention-free mapping finishes with little overhead, but reveals its deterministic maximum latency using exclusive transmission slots. The local data push case unsurprisingly finishes in about half the time compared to an interest request and remains largely unchallenged. To conclude, contention access should be retained for management traffic. The more reliable contention-free media access should be used for interest transmissions and ideally also for data. If the deployment scenario allows it, a local unsolicited push greatly improves the performance. Based on these results, we have designed our LoRa-ICN convergence layer. We have added a node registration feature that takes place after a node joins the DSME network. A node registers an individual name prefix at the gateway, which acts as a node custodian and LoRa data cache. Data provisioning by sensors should utilize the local data push with contention-free media access, while the gateway only caches data from registered nodes. A slot-based MAC naturally assists prevention of DDoS triggered by publishing LoRa nodes. A malicious node can simply be muted by the coordinator, deallocating its transmission slot. Conversely, interest requests from the internet should only be forwarded by the gateway if the name falls under a registered node prefix. In practice, missing entry in the forwarding information base automatically provides that with ICN. The gateway additionally needs to lift timeout values to the long latency domain. This prevents duplicate interest forwarding to the wireless link using built-in ICN interest aggregation. Although not directly discussed in this talk, a node control scenario from the internet would be realized with that same principles. For the MAC mappings, we utilize contention access only for node registration and sporadic traffic, which includes slot negotiation. Contention-free media access showed the best compromise between latency, reliability, and throughput and should be utilized otherwise. Beacons, albeit excluded from this talk, provide a unique and efficient opportunity for downstream multicast scenarios, for example firmware updates to many LoRa nodes. Now to conclude. In this work, we have designed a new LoRa system to overcome LoRaWAN limitations. we presented LoRa-ICN, which leverages existing technologies, namely DSME and ICN. We have contributed a complete simulator with OmNet++ and the INET framework. Our design shows that DSME provides horizontal scalability, robust media access, and low-power operations for LoRa nodes. Built-in ICN mechanisms, such as selective forwarding, interest aggregation, and caching, help offloading the challenged LoRa wireless domain. Our extended gateway acts as a LoRa node custodian and connects LoRa networks efficiently to the internet. In future work, we will extend our analysis to more complex deployments, including multi-gateway, multi-consumer, and node-to-node scenarios. We will further investigate ICN security with LoRa, the unsolicited push scenario in particular. And finally, we will implement and evaluate the system on common IoT hardware. Thanks for your attention. We support reproducible research. Our code is available on GitHub.